Okay, so good afternoon. Today we will talk about some of the critical speeds in shafts. That was the portion which was left. I think it will take 15-20 minutes, and then we'll move on to something called limits and fits. So once we design a shaft, how do we basically manufacture it? And we know that shafts is manufactured somewhere else, bearing is manufactured somewhere else, but still they fit, right? So how do we ensure that, how do we evolve a standard for different engineering applications? This is what we'll discuss. So let's start with critical speeds first. So critical speed is if the rotating shaft, if the centripetal force, if m, okay, if m omega square y plus e. So why is the deflection? Because shaft will always have some loads, right? So because of this loading, so if I have a shaft and the shaft has bearings here, a bearing here, and there is some gear mounted, some sprocket mounted on it. In some cases there can be an impeller, right, or a turbine. So what will happen is there will be loads here, right? So because of this there will be some deflection. Because of these loads and even self-weight, there'll be some deflections, and there will always be some eccentricities also, because whatever we do, we cannot have a perfect alignment, right? So we'll have some eccentricities there as well. So because of this, and then this will be balanced by the elastic restoring force. So elastic restoring forces will be nothing but a force F, which you can say some sort of stiffness times y. I'll derive something based on this, and I'll basically show how does the critical frequency is derived and what happens at critical frequency. So if we will use some formulations for this, but for now let's go ahead. And at some speed, omega is equal to omega c, the y increases significantly. This y is deflection. The deflection is significant, so it will almost start to whirl. The shaft will show some sort of a whirling phenomenon, right? So the shaft rotates and there will be a whirling. This is something which needs to be understood, because if the shaft starts to whirl, in that case what will happen is it can damage the rotating equipment, it can damage the shaft, it can also damage the turbine or whatever we are using. So we don't have to go anywhere near that critical speed. And even if we go it very fast. So we do not really dwell upon in that regime, because there can be very significant problems with that. So critical whirling speed is actually a function of shaft dimensions. Sorry, let me take this back. Shaft dimensions, the shaft material, right? Because E, so say length, E, and shaft loads, M, which is the mass mounted. So all these things will have an effect in determining what kind of critical speeds you would get. And of course, the configuration where the load is loaded, right? Whether it is a center or it's off center. So all these conditions will govern what kind of whirl or whirling speed or critical speed you will get. This is an entire field by itself, rotordynamics, but what we will do is we will just brush upon it so that we understand the criticality of the situation, right? These things need to be accounted for whenever we use shaft designs. So basically, very simply, what you can do is, all this, that m omega square y is equal to ky. So basically, I know that omega or 2 pi nc frequency, omega or 2 pi nc will be equal to root over k by m, where k is stiffness and m is the mass. So critical speed should be nc is equal to 1 over 2 pi root over k over m. And if we know that nc is equal to 1 over 2 pi root over k, I know that m, if you see, so basically, if we know that there is the force, if you know force is equal to mg, right? which is equal to ky. So basically I can use sorry, k over m is equal to g over y. So I can do this. The gravity times divided by y will be the natural frequency. This is one way to understand what will be the static deflection under the concentrated mass. So this y is the deflection under the concentrated mass. Then you will be able to find out this. So there is another method called Raleigh's method. So Raleigh's method of lumped mass, what you can do is you can basically find out for any ensemble of lumped masses, you can use the same concept where omega is equal to g sigma wi yi divided by sigma wi yi square. So wi is the weight at ith location and yi is the deflection at the ith body location. So if you have these kind of lumped masses, right, if you can assume that at this location there is mass w1 w2, this is y1 here, deflection, y2 deflection here. If we can find that out, that there is a lumped mass and deflections at every lumped mass, I should be able to find out using Raleigh's method what will be the world velocity or what will be the critical speed, right? So this is one way to do it. I'll give you some other methods also and basically explain how do we get the critical velocities. So basically I'll derive so from beam theory I can do something like this. Is I know m is the mass, m is the mass, m is the critical speed, g is the gravity, o is the centroid location, g is the center of gravity location, l is the length of the shaft, e is the modulus velocity, I is second moment of inertia, and second moment of area or moment of inertia, and y is the deflection and deflection of the with shaft rotation, and omega is the speed of the shaft. So basically what I'm assuming is I have something like this. I have a shaft like this. Which is loaded with mass m, and it has a deflection y at the mass m and some eccentricity. So basically y plus e I can say. Right, there'll be some eccentricity and some because there will always be eccentricity. I cannot align it perfectly, right? So there will always be some eccentricities. So now what I can do here is, as I said, and I also know that m omega square y plus e, this is the centripetal force, and then this is balanced by the elastic forces, which is ks times y. Right, and I know that root over ks by m will be omega c, right? So I can if I were to see this, what I will get is omega c square is equal to ks over m, right? So if I do this, I'll get m omega square. Sorry, let me just take m out. Y square plus e is equal to ks over m times y. Right? Now ks by m is nothing but this is the natural frequency. If I know the elastic stiffness and the mass, point mass at that point, I should be able to find out what will be the natural frequency. So basically omega square y plus e is equal to omega c square y. Let's simplify this further. Right. So this is the equation which I have. And y typically in this kind of a conduction, y is basically something like, if a simply supported thing is there, so y is FL cube by 48 EI. If it's a cantilever, y will be FL cube over 3 EI. For a general condition, I can assume y is some constant L cube over EI. That I can safely assume, right? Because that's how the shafts are there, right? So this is the concept. I wanted to basically show how do you get. So basically, if you do all this, you should get something like this. So I have, sorry, let me go back. So I had this equation, right? Omega square y plus E is equal to omega c square is equal to omega c square y. So omega square y, right, and plus omega square E is equal to omega c square y. Let's go ahead and do this. So basically I'll get omega c square minus omega square y is equal to omega square eccentricity. So basically, if I want to find what will be the deflection, deflection will be omega square E omega c square minus omega square. So this will be the deflection. Now I'll wait here. Do you see this equation? Can somebody tell me if omega approaches omega c, what happens? What happens here? If omega approaches omega c, what do you think will happen? Any guesses? You can type in the chat box, or you can unmute yourself and tell me. Either way is fine. What will happen? What do you think? If omega approaches omega c, what will happen? What does this equation show? What kind of failure? Like what physically what will happen? What you understand what y means? So y is nothing but the deflection. Failure may not be the right word, but physically I'm asking what will happen. So this is my y, the deflection of the beam. Resonance is a very good answer. So what happens is this y will become very, very high. Right? Y will become very, very high the moment you go. So basically it means that your thing will start to sway like this. So it will be like almost like a rope, right? The shaft will start to whirl at so y will be very, very large. Y will be very, very large. You can see if you plot this at omega is equal to omega, it will become infinite, right? But even when you get very close to omega c, a lot of damage gets done because of this high deflections right at the load. Where the load is, you'll have very high deflections, right? So this will create a lot of problems. And that's why the critical speeds need to be understood, because critical speed, as you said, failure will happen, but failure will happen because of this high deflections. So we don't want that to happen. And imagine this happening at 20,000 RPM, 50,000 RPM, what will happen? It will just go pieces. It will just break, right? So failure would happen, you're right. But failure happens because of this deflection. The deflections at omega c is equal to omega. If you plot this, you go ahead and see what will the deflections will become very, very high. And theoretically, at omega c is equal to omega, it will become infinite. Any questions here? And then we'll go to the next thing. Any questions here? So you need to be able to determine this critical speeds. So let me ask you a question. Now, how do we determine the critical speeds for different conditions? How do I do that? Any guesses? Any suggestions? Some suggestion should be there, right? You should be able to give me some advice. How do I get this? E and I will be different. Let's assume E and I deflections will be different, yes, but I want to find out the natural frequency. It will be a function of E and I, agreed. It will be a function of E and I as well. But I want to find out, how do I find that out for a given condition? Let's take a condition. Let's do this. Let's take a simple condition for this, for a cantilever condition. Can I find something out for cantilever? So I said that omega c is equal to root over k by m, right? What will be k for this kind of a situation? No, not experimentally, not experimentally. So what you are suggesting is that I increase the direction velocity and find out what the deflection is. That's the experimental way of doing it. It's very damaging. I should be smart enough. I'm an engineer, right? I should preempt it, right? So I know that this is Ks over m or stiffness over m, right? What is the K for this kind of a configuration? For a cantilever beam, what do you get for K? नहीं रे, EI नहीं. EI is a flexural stiffness. EI is the, yes, some constant times. So basically he is right. The final answer is right. PL cube, or basically Y or delta, is equal to PL cube, P being load, point load, PL cube over 3EI. Right. So K will be what? 3EI over L cube for this condition. Right. So if I know what is K, so 3EI. So basically, if I know the point mass, I can say 3EI over ML cube should be my natural frequency, omega c, and omega is equal to 2 pi NC. So NC will be equal to 3EI by ML cube under root divided by 2 pi. This is what you get, right? So I can calculate it, but sometimes it is difficult, right? I don't remember all of these. So this is for cantilever shaft with a disc in the end. Central disc with long bearings. So long bearings, you can basically assume it to be fixed. This is a fixed kind of configuration. So I don't know if anybody remembers what is fixed beams deflection with central loading. Anybody remembers that? Fixed beam. For simply supported, for simply supported with central loading is PLQ over 48 EI. But if it is fixed, what do you get? This is for a simply supported PLQ over 48 EI delta. If there is a central loading and simply supported beam is there. But you're right, it will be some constant as EI over L cube. Some constant times E over L cube. So this constant, if you see here, you get 192 for this kind of a bearing. For this kind of a bearing, you get 190, where you have long bearings and a central disc. Right. So, and then there are other configurations. Central disc with short bearings. This can be assumed to be a simply supported configuration. Now, non-central disc with short bearings. Again, these can be assumed to be simply supported. These are very gross, very, I would say, first order approximations. You should remember that. right? These are first order approximations, and I can use these very effectively. I'll actually show you a method with which you can use it very effectively to find it for a system. Again, simply supported, right? So this is 48 EQ, 48 EI over LQ, right? And then this is with some off-central short bearings. The short bearings, you can assume it to be simply supported. Long bearings, you can assume it to be fixed condition. Cantilevered shaft, if you see with self weight, this is what it is. If you know the load of the, if you know the mass of the shaft, this is what it is. Shaft between bearings, so the shaft has self weight, you will have this kind of natural frequency. Now, why am I telling you all this? So shaft also with loads also, right? You know that shaft between long bearings, you would get something like this. That is self weight of shaft. Actually, this is mass per m is, sorry. Just 1 second, let me go back. Right? Okay. How did this happen? There is one more slide, somehow it is missing, but I'll write it for you. Okay. So there is something called a Dunkirk method. There is something called Dunkerley method. Dunkerley's method. And it actually does something called superposition. Superposition. So if I have this, say, a shaft with bearings, long or short, here there is a bearing, here there is a bearing, right? And then I have M1 here, M1 here, there is another M2 here, there is M3 here. So there are these 3 point masses, and then there is a shaft, right? So I can say M1, at M1 there is deflection Y1, M1, Y1, M2, Y, and then there is mass MS, shaft mass also YS, then there is M2, Y2, there is M3, Y3. Right? Now, what I say here is I can use these formulae and do the superposition. You know, I have what will be the, so my basically I can have a formula, something like this. If I know the individual critical frequencies, I can juggle and I can say 1 over entire system, 1 by NC square is equal to 1 over NS square. So I'll take just the shaft in the bearing and calculate for the shaft, right? 1 over NS square for just N1 at the same location for M1. I can get 1 plus N1 square, 1 plus N2 square. So this way, till in this case there are 3, so I will do 1 plus N3 square. But I can do it for any number. I can actually get for different components if they were alone. If they're alone in the system, this will be the natural frequency. So I can use the Dunkerley's method to determine what will be the natural frequency of the system by using this kind of a methodology. It's a very simple one. Ideally, if you want to use it, you can use finite element method. It's much easier these days. So, but then this will also give you a decent first order approximation. Okay. Any questions? I'll take some questions now before we move on to the next thing. Any questions, which is anything you want to talk about, discuss? I'll wait for some time. We can have some discussion, and then we'll move on to something else, which I think you know a little bit, but I'll still brush you up. Any questions still here? So you understand what Dunkerley's superposition method says? So Dunkerley's method, it just says that you take as if there was only shaft there, then only M1 was there, M2 were there, and you have all these formulae, right? You have all these formulae. You can use for M1 this formula, and for M2 also this formula, for M3 this formula at different locations, because you know A and B are different for M1 and M3, and then just sum it up. Any questions? Anything which you want to discuss right now? We'll do it before we close the shafts thing. And then we'll go to something called limits and fits, which I believe you would have done something in ME338, but still we would brush up a little bit. Any questions? Nothing. If you have any questions, feel free to type in the chat box. If not, we'll move to the next thing. Good. If there are no questions, let's move to the next thing. Why are beams and shafts different cases? I didn't get you. Can you qualify this? The shaft is a kind of a beam, right? You model the shaft as a beam. What do you mean by different cases? Perhaps I'm not getting your question very well.
Sir, I missed why are we not considering the same NC formula for both of them?
For both of it, as in?
For the beams as well as the shafts.
No, where is beam? I'm talking only about shaft, right? Where did we discuss beams? I'm just using the beam formulae for getting this, for modeling the shaft.
Okay, all right.
Right. So I'm using those formulae for beams because shaft is nothing but a beam, right? If the static shaft, if you look at the static shaft, right, the elastic deflections between a bearing, a shaft is there. It's like a beam which is simply supported, right? A short bearing can be modeled as a point load, and a long bearing can be modeled as a fixed support, because it will be fixed because the slope will be 0 at the bearing. So it's like a fixed support. That's all I was saying, that we are using the concepts of beam theory to model these shafts to get the natural frequencies. And Dunkerley's method says that what you can do is you can assume that each of them are independent and just sum it up in so basically 1 over a square. So it's an inverse of square. If you do it, you will get the natural frequency of the system, because now system will behave. System is a composite thing, right? It can have multiple impellers. Pumps can have multiple impellers, or your shaft can have multiple pulleys or multiple gears mounted on the shaft, right? So then in that case, you will have to have a composite natural frequency. How do we estimate that composite natural frequency is what Dunkerley's method says, right? That's what I wanted to give you. So you basically assume that these are all individual cases, find out for each case, and then take the inverse of squares, take the inverse squares and sum it up. Okay. So beams and shafts are not different gates. We are assuming shafts to be beams and using the beam theory to calculate the natural frequencies of the shafts. Did I make it clear for you, or you still have doubts?
Yes, I understood.
Great. So then what we do is we go to something called limits and fits. Okay. So I'm assuming you all know what is limits and fits, right? You have done in ME338 class, have you or no? Do you know limits and fits? Before we start, I just want to check. Have you heard about limits and fits? Something called limits and fits. Have you heard of this term? Anybody? You can just use the chat box, and if you guys know about limits and fits. Have you heard of this term, limits and fits? So what does limits and fits do? You have done something in ME338 with limits and fits? Some of you may have not. So I'll talk about both the limits and fits and also how do you gauge them. Both we'll talk about a little bit. Okay. So what is limit? What are limits and fits? What does a fit mean? Can somebody tell me, since you have done it? Can somebody explain what is a fit? And then we'll talk what is a limit. What is a fit? Anybody?
So basically, it is I think we read about three types of fits based on the shaft diameter and the diameter of the bolt of the nut, I think. And
Hole is fine. Nut you don't need to worry about. It's just a hole and shaft. Any
yes.
hole, any shaft. So what kind of three fits are there?
Um, so I think clearance fit, interference fit, and there's a fit in between. So transition fit, I think.
Yeah. So clearance, very good. Clearance fit and interference fit and transition fit. Right. So I'll just explain a little bit about how do you go ahead and how do you decide what kind of fit to use. So fit basically means that if there are two mating things, right? If you have a shaft and a hole, sometimes what happens, it goes very easily, right? So you have a lot of clearance. Sometimes what happens is it is sometimes it goes, sometimes it doesn't go. So that will be your transition fit. Right, so the band is such a way that sometimes it's very easy to go, and sometimes it starts to interfere under certain conditions. And in some cases, what will happen is your lowest, shaft interferes, meaning the hole, right, the largest dimension of the hole, right, and the smallest dimension of your shaft. So smallest dimension of shaft is larger than the largest dimension of your shaft. Right. In that case, what will happen? It will always interfere. But in some cases, because whenever you give dimensions, right, you give dimensions with some range. You'll give a tolerance. This is the limit. The limit means if I am making a 50 shaft, right? Because now I have designed the shaft. Now I have to make a shaft, right? I have to tell the shop make a shaft. If I say make 50 plus minus, say 1 right? So the lowest dimension would be 49, the highest dimension will be 51. Now I say make 50 mm plus minus 0.1. You will say it's okay, 0.1 is 100 microns, still okay. Now I say make 50 mm plus minus 0.01, 10 micron tolerance. Now I say make a 50 mm plus minus 0.001 mm. Do you know what's the difference in the cost would be for three of these? Any idea? Just a guess. If I ask to make somebody make a shaft which is between 50 mm and 49 mm, and then I ask make a shaft which is between 49.9 mm to 50 mm, to 50.01 mm, right? That would be, this will be what, 49.99 to 50.01. So basically this is 0.99201. So there is a 100 micron. You have a 100 micron tolerance, right? No. What is the tolerance here? 0.1. What is the tolerance here? So here there is 10 micron tolerance, I believe, right? Here there is 10 micron tolerance. This is here 49.9 to 50.1. So here there is 0.1. So 49.9 to 50.1. So here there is about 200 micron tolerance, right? Plus minus 0.01 is you have 200 micron range. So minimum can be 49.9 mm and maximum can be 50.1, right? Now you can go with 20 micron. Now you can go with plus minus 0.001 will be 2 micron tolerances, right? Any ideas? If I give, I'm making, in all cases I'm making 50 millimeter diameter. Ideally I'm making 50 millimeter shaft. In one case I'm giving 1 mm tolerance plus minus 1 mm. In other case 0.1 mm tolerance, other case 0.01, and finally 0.001. Can somebody just give a rough idea? What will be the price difference between the two, between the first one and the last one? Last one may not even be doable, actually. You need a super precise machine to be able to do that. Maybe a very precise grinder may be able to do it. Super precise grinder would be able to do the last one. You get what I'm trying to say here? By defining these numbers, right? What is it I'm doing that I'm making 50 millimeter shafts, but in one case it's very easy. The other case it's almost extremely impossible to do it. So what is it doing when I'm giving a tighter and tighter tolerance? Any answers for this? You can just type it. What does this do? So just to give you some idea, the cost for this one, if I'm making a shaft, maybe say the cost of steel, if you go ahead, it will be some 80-90 rupees kg. And you do a normal lathe, you can take a manual lathe and get that precision on this one with for plus minus 1 mm. You'll probably pay another 500 rupees. So it is 600 rupees. You will probably be able to get this kind of a 1 mm thing. If you want to go to 1 micron one, plus minus 0.1 plus minus 1 micron one, you know the cost can be tens of thousands of rupees for this one. Tens of thousands of rupees, even more expensive than that for just a small shaft, say a kg shaft. So your price, just because you define a tolerance, your prices can go exponentially. So you have to be very careful in assigning these numbers. You see on those drawings, right? People write these numbers. So these numbers can drive the cost exponentially. So how do I choose what to put there? Any answers? Now you know that I cannot put anything. If I put very tight tolerance for no reason, I'll make something that is 600 rupees, 20,000 rupees. The material still is actually 100 rupee material, but the processing cost will get into tens of thousands. So there's an exponential increase in the price. So how do we go ahead and choose these numbers, these tolerances? What would be your driving point in these tolerances if you have to choose one? How do I go ahead and choose it? Any guesses, any answers? Just a guess is fine. Cost versus performance plot. But okay, but how do I choose what performance I want? What drives my performance? If it some performance index, tolerance range is, you have to decide that, right? Because tolerance range is driving the price. If I take the tolerance of 1 mm plus minus 1 mm, it's almost I said 600 rupees. If I take plus minus 1 micron, the cost is tens of thousand rupees. So tolerance I have to choose somehow, right? Performance index, I kind of get it. More tolerance will give less performance. No. Yes. Application. What is the functional requirement, right? Why would I give a tolerance of plus minus 1 micron? Can you tell me a place where this might be important? Plus minus 1 micron? If it's a super precise bearing, going at say 100,000 RPM, I need these tolerances. Aerospace maybe, but there are a lot of other applications, especially applications where you have high rotating speeds. Aerospace can be one of the applications, but aerospace are larger applications, so you cannot have such tight tolerances. But where you have a functional requirement, the answer is the functional requirement. Unless and until there is a functional requirement, I will never ever give a tight tolerance. Never ever. As an engineer, my first idea should be, yes, fluidics. In some cases, you need tolerances, but microfluidics, typically there's no mating parts there, right? So you just have to make accurate channel. So if there is a mating part, that's where your tighter tolerances come, because tolerances will always come into aerospace. Is a very good answer. Aerospace you need. Medical devices sometimes you need, but unless until you have a mating part, your tolerances may not be that important. But yes, you need tolerances, true. But if you need tolerances, typically high tolerances will only be in high rotational speeds. If it's a static equipment, a medical device which is static, you don't need that kind of tolerances. You don't need. So if you have say in some implants, yes, you may be right. If you're doing a hip implant, you want very tight tolerances because you don't want it to come loose, right? So there are some applications where there is a mating surface and there is a functional requirement. So this functional requirement can be very high rotational speed, or conformal fit, as in some of the implants. Conformal fit, if there's a conformal fit where you have to have a perfectly fit femur in the ball, right? So ball, some sort of a ball joint, so you need to have a ball and socket perfect, so that there is minimal wear, because if there is a lot of loose things, then there can be wear and it can be fatal for the patient, right? You have to go ahead. If there is wear particle coming, then it can create some bioirritation, and it will have to be replaced. So you need these tolerances in some cases. If I have some very precise mating surfaces, so in conformal contacts, in mating surfaces, high rotational speed devices, there you need in functional requirement. So you have to understand the functional requirement. Your functional requirement drives the tolerances. So you have to be very clear. Functional requirement drives the tolerances. So as a designer, you should always think whether I'm giving a tolerance, whether it makes sense to have such tight tolerances. If not, give a tolerance which is acceptable, right? Drives the tolerance. Right. Now, so if you see in any manufacturing, finally you've designed the shaft, it has to be made. So there are certain aspects which you need to understand. The first thing would be you have to sell. So there's a marketing aspect. A functional aspect is what you get from the designer. That's the designer's prerogative. What is the function? A manufacturing engineer doesn't decide this. This is decided by the designer. Right. So the designer decides that this is the functionality and he says that, okay, I want these tolerances. And the job of manufacturing engineering would be to make that. Sometimes he will say, I cannot make it. If the designer decides to have a unrealistic tolerances, as I said, plus minus 1 micron, he will say, I don't have such kind of a precision grinding machine. I can't do it. Right. Then there are operational aspects. Then there is durability and dependability. So there's a reliability, economic aspects, manufacturing aspects, and this is where we have to start making it and have to identify what kind of fits we get. Read those drawings and then identify, oh, this is this fit. Okay, and then aesthetics. So I can make these tolerances or these surface roughnesses very, very good for aesthetics, but that's stupidity. As a designer, you should always see and specify surface roughness tolerances only if there is a functional requirement. Making super smooth costs money. Polishing, if you do super polishing, can be a fairly expensive process. Any finishing process, whether it's grinding, honing, polishing, these are super duper expensive processes. And these can be more expensive than what you, so finishing can be more expensive than the entire machining process. You make the product, it's cheaper than what money is spent in finishing the product. Okay, so all these things you have to understand. That's just for aesthetics. Don't specify surface roughness because it will cost. So you have to live with some sort of surface roughness. But if it's a functional requirement, go ahead, specify whatever tighter tolerances or surface roughness are required. Okay. So basically, whenever you do metrology, when you design something, so first aspect is functional requirement. So you understand there is a functional requirement. I want some degree of fit, right? And then based on that, I define what will be the fit. Because I have to assemble the part, right? So the fit, does the fit need to be interference? Clearance, or transition. There are three kinds of fits. Then you have to give. So now once you have defined the fit, right? Then you have to give some tolerance, because what this fit does is it basically defines how are the. So if say this is the band of the dimension of say shaft. Let me just show you. So I have a shaft like this. So when I make the shaft, right, I cannot make it. I set out to make say a 50 mm shaft. Can I make a 50 mm shaft? Is it possible for me to do 50 mm shaft? Pakka 50 mm. Is it possible? Can I do that? Bang on 50 mm. Is it humanly possible? No, very correct. I cannot. There is no way, because I can't even measure it with that accuracy, let alone making it. Right? So there will always be some band in which I will make. So let's assume that this is the lowest I can make, smallest shaft. This is the smallest shaft I can make. This is the smallest shaft, and this is the largest shaft I can make. Permissible. And then I have, so basically what happens is, and there would be some zero, so some zero line which will be the size, the basic size which I have defined. So this will be, if I go ahead and do this, this will be this kind of difference between the smallest and the largest is called the tolerance. This is for shaft. Same thing can be there for hole. So imagine I have a bigger hole. Let's assume that I make a hole which is bigger. So I have, my hole is this big. The smallest hole is here. The largest hole is the top one. So I have these two. And the nominal size, let's assume that the nominal size was somewhere here. This is what we wanted to make. This is what the nominal was. Nominal size was this, but shaft we made both less and hole we made both large. So basically, this will be, if we make something like this, this will be a clearance fit, right? And this dimension between the smallest and the largest dimension, difference between the thing, is called a tolerance. And I'll basically tell you how do you go ahead and identify those tolerances. It will again be a functional requirement. How do you identify the fit, and also what kind of tolerances you want, how close you want the smallest and the largest dimensions be. So this is what, and then manufacturing processes. So based on these, you will choose manufacturing processes, because what will happen is, if you keep it tight, the tolerances tight, the cost of manufacturing goes exponential. Because then you'll have to use some very different machines and different processes to do that. Okay, and the cost of manufacturing is always correlated with the tolerances. The tighter the tolerances, the more expensive is the cost of making a part. Okay. So this is what I wanted to give you some feeling as a designer, that don't use those tolerances or whatever you specify. It has to be driven by a function. Okay. The tighter is not better always. That's what you have to keep in mind. Tighter is not better. Tighter, if it is required by functionality, yes, go ahead and do it. If not, don't choose a very tight tolerance. So basically, how do you go ahead and do it? I'll solve some problems also at some point of time, but you have to do, first is appropriate fit based on functional requirement. I'll tell you how to do that. Then you basically use some type of shaft and hole. Then you get something called tolerance grade. So tolerance grade you basically find out. So tolerance grade would be how big is this dimension between the lowest and the highest one, between the smallest and the largest one. And then there is something called standard evaluation of standard tolerance unit, which I will show you how to do that as we go there. And then based on that, there are various grades. There are IT 01 to 16, 01 to 16. This is the largest. This is the tightest. These IT01 is very tight. These are only used for gauges, for measuring devices. Right? At some time, you also need to make gauges, right, to measure something. Those gauges have to be extremely tight tolerance, because they are a metrology device. Right? And then you basically find out the limits of tolerances. So this is the flow chart which is there, and I will actually do some problems to show you how to use that method. So basically, there are two concepts which all of you would know. There is something called precision, and there is something called systematic error. Can somebody tell what precision means? What do you mean by precise? Is precision and accuracy the same thing? Is being precise same as being accurate? Why not? How are they different? Okay, very good. Precision means low variance. So basically, I have two kinds of people, right? Two dart throwers, right? One dart thrower throws very close to the bullseye. Here, 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 here. The other dart thrower is off, but he throws very, very close. Right? Now what happens is this guy has a systemic error. If you fix this error, he's bang on target. Right? He's very repeatable. He's very, very repeatable. But this guy doesn't know what he's doing, although he's not very bad, but he just doesn't know what he's doing. So fixing this, not easy. Fixing this, easy. Okay. So low variance people are always easy to handle because you know there is one problem with them. You zero in and you fix it. But this kind of a thing was very close but all over the place, not easy to fix. So typically what happens is the way you define accuracy is repeatability. Repeatability plus systemic error. Right? Systemic error is how far you are from the mean. So this is the mean and how far the mean is. That's the systemic error. So square of systemic error and square of repeatability under root is your accuracy. So accuracy is also a function of systemic error if your mean is off, and then the repeatability. How far repeatability is basically standard deviation, as he said, low variance. Okay, so this is something which you guys know. Now this is what I want to give you some definitions here. So the definitions are, first thing you need is something called zero line. This is zero line. Zero line is the line that corresponds to basic size. So basic size, I say 10 mm, 10 mm, 50 mm. These are basic size. I want to make a 50 mm hole. My problem is I can never make a 50 mm hole. I want to make a 50 mm hole. So what I will do is I will have some tolerances over it. So my actual basic size corresponding to my size, I can ideally imagine, right? My basics, I can make it on paper, may not on the part. So I can basically say, imagine that this is my zero line. My zero line corresponds to basic size. So wherever the zero line passes is the basic size, what size I set out to do. Now what will happen is I will always have some difference from the basic size. Now there is something called a lower deviation and an upper deviation. For shaft, the upper, sorry, for a shaft, the upper deviation is called small es. For the hole, the upper deviation called capital Es. So these are the definitions. This is how you actually write the upper deviation. So upper deviation is the topmost point. So upper deviation capital EI, capital ES, the upper deviation. The upper deviation is capital ES and the lower deviation is EI. So S is for basically surface. So basically if you see that the upper deviation is this from the zero line wherever the upper deviation of surface lies. For hole we use capital, all the dimension, all the things are capital for hole. For hole you use capital letters. For hole capital spelling is wrong, capital letters, and for shaft you use small caps. Right? So ES. So ES will be, so this is small es is the top surface right here. So this is ES, this is called upper deviation. Upper deviation of shaft ES, upper deviation ES is the small ES is the this is ES. Sorry. This is the upper deviation of shaft, small ES. For hole, the upper deviation, the capital ES is this. This is the capital ES. So these are called upper deviations for shaft and hole, ES, capital ES for hole, small ES for shaft. Then there is lower deviation. So lower deviation is EI, capital EI for the lower portion of the, so the corresponding to the D min. So D min, capital D min and capital D max. Capital D max is for is the largest dimension of the hole, and small and D min is the capital D min is the smallest dimension of the hole. So this is the largest dimension. If you see, this is the largest dimension, and this is the smallest dimension of hole. So this is D min, and this one is D max. Right? Let me just clean it up so that I can go and show. So ES, you know, ES is upper deviation, EI is the lower deviation. Lower deviation means the lower, the inner portion of the inner limit of the hole and the inner limit of the shaft. Both in both. So EI corresponds to your D min and D min, both. So if you see, so EI corresponds to D min and ES corresponds to D max. Okay. So you know ES and EI, and you know zero line, you know basic size, and basically this is, and these can lie anywhere. These can be clear. This particular example is for clearance. So if you see, if my band, so here, this is the hole. What if the hole like this, shaft like, let me make a thinner one so that it's more clear. And shaft is like this. What kind of fit is this? Can somebody tell me what I have drawn? So this is my hole. This is my hole and this is my shaft. And then take another case where this is the hole, this is the shaft. This is the hole. So this is the right now in first case you saw, is this interference? What is this one? The third one. This is the hole, this is the shaft. So this is second and this is third. Both are interference? Are 2 and 3 both interference? Or 3 is interference or 2 is not, 2 is something else? Yes, in 2 it depends. Sometimes it will be clearance, sometimes it will be, so imagine if my hole size is here, shaft size, if my hole size is here, shaft size is here, it will go. So this is 2 is transition. 2 is transition. This is what is called transition. Sometimes it goes, sometimes it doesn't go. Is transition. So this is the example of transition, what I'm showing. There is an overlap between the tolerances. So if you have an overlap between the tolerances, this basically means that this is a transition. Sometimes it goes, sometimes it will not go. If there is no overlap, if your shaft is always bigger than your hole, so if this is shaft and this is hole, then it is always interference. Okay. But then these are the things which you will use, and there are two systems, hole base and shaft base. So you can either take shaft as the reference or hole as the reference and do it. It doesn't matter. Okay. And then in this case, there is something called fundamental deviation. So deviation from the zero line, like ES or EI, ES or EI, they will be called fundamental deviation. I'll tell you what fundamental deviation means, because that is the deviation which I'm looking for in a standard. So there are standards, and these standards identify either capital EI or capital ES in case of hole based system, or capital or small EI and small ES in shaft based system. And they will say one of these, in some limit, one of these will be fundamental deviation. In the other one will be fundamental deviation. So you'll have to look at the standards and then decide what will be the fundamental deviation. But fundamental deviation will either be capital EI, capital ES, small EI, or small ES. So basically, the deviation from the zero line of the Dmax, Dmin for the hole and the shaft, one of these is the fundamental deviation. It changes as you go. For certain range, one capital EI is the fundamental deviation. For certain range, capital ES is the fundamental deviation. I'll show you how it works. Okay, but then one of these can be fundamental deviation. So basically, let me list out the definitions. I have described what the definitions are, but let me list it out. So zero line is the line along which represents the basic size, and the zero is the measurement for upper and lower deviation. So zero line is just the measurement for upper and lower deviations. Basic size is the size with which reference to upper and lower are defined. So basic size is the size. So you have some size which you have decided. Basic size is that size, and typically these are these will be some ranges are there. I'll show you how do you define. There is a range in which you can find out these sizes are there. Okay, but then this size can be 5 mm, 8 mm, 9 mm, 10 mm. These are basic size. I'm trying to make some. It will not be in fractions, of course. It will be in integers. And then shaft and hole. These terms designate external and internal features of a shape, not necessarily cylindrical. So in your mind, it is cylindrical, but it doesn't need to be cylindrical, because they can have any other fit. It can also be oblate, right? These are just, you are trying to have a mating part. They need not be cylindrical. Let me emphasize, these are just for mating parts. So you're basically assembling certain thing. This assembly can also be non-cylindrical. Okay. Let me be very clear that this is required for assembly. Then hole designations are there. I'll tell you what they mean. A, B, these are ISO standards as well as IS standards. Both are same. We have taken from ISO standards, and there are called A, B, C, D. These are hole designations, and these hole designations basically mean what will be the fundamental deviation. So basically, hole designation assigns some fundamental deviation. When I show you, it will be more clear. But hole definition is fundamental deviation is defined by the hole designation. And same thing, shaft designation. Again, the fundamental deviation is what you get from these shaft designations A, B, C, D. Okay, I'll show you what it means once I show you the actual standards. It will be more clear if you see the actual standards. So there are 25 numbers, both ISO and IS. So let me now just read out what the definitions are. Upper deviation is the algebraic difference between the maximum limit of the hole, maximum size of the hole of the shaft, and the corresponding zero line, ES and ES. Lower deviation is capital E and small ei, the algebraic difference between the zero line and the minimum size, right? The minimum limit. Fundamental deviation is one of these will be fundamental. I'll tell you which one. So in one set of range till less than h, one is the fundamental deviation. After h, the other one is fundamental deviation. I'll show you what it means, because this you need to see to be able to figure that out. Okay, the algebraic difference between upper and lower deviation is called tolerance. So what I was making this, the difference between the d max and d min, that's called tolerance. Okay, this is the band which is there. Limits, there are two. So basically tolerance governs what are the limits, the lower limit and the higher limit. From the bottom to the lower tolerance, bottom to the top tolerance would give you the limits of the sizes. So this is the limit of the sizes, my d min, d max for shaft, and capital D min and D max for hole. This is for shaft. This is for hole. Okay. So the shaft and holes have zero fundamental deviations. The basic hole has zero lower deviation, while the basic shaft has zero. So basically, basic line. The basic line I have shown is whatever you have decided, like whatever numeric value you are giving. 50 mm shaft is the basic shaft. So that's where you define everything from. So this is how basically it means. So these are transition, right? This is interference. This is the shaft. Shaft is bigger than the hole. So this is a hole-based system. You fix the hole and see the shafts, or you fix the shafts and see the hole. So basically, either you can have hole-based system or shaft-based system. Typically, we have hole-based system. That's more popular. Okay, but then either ways is fine. Doesn't really matter. You still use the same things, same combinations. So this is what I was talking about. These are the schematics of grades. When you talk about, so basically, if you see, this is very clear. This EI is fundamental difference till H. So till H, the shaft is the lowest, the D min, the lowest diameter of the shaft D min is greater than the zero line. So whatever the dimension you have decided, so if you have decided 50 mm, my zero line is say 50 mm, it's the lower limit, the EI is much farther. So it's much larger than 50 mm. So it's like 50.2, 50.4, 50.5, something like this. And what happens is, so if I have a shaft and a hole, can somebody answer what will be the fit here? So this is the A shaft. The A shaft, the fundamental deviation is this. So, and then tolerance I can define whatever. So there are two things. One is the grade or the fit, and then the tolerance. These combined. So tolerance would be what will be this band will be tolerance. Fit will be what will be the location of EI from the zero line. This is called fit. So there's a fit and a tolerance. The fit is given by this letter grades A, B, C, D, and till H. What happens is my EI is above the zero line. Very good. So you will have AA will be very loose clearance, very large clearance. As we keep on going tighter and tighter, let's say H. If I have H, what happens? At H, what will happen? So that was confusing. So I picked up a few of those. A is up than zero line, A is below. So hole and shaft are just very symmetric. So in hole it's EI and in shaft it is ES. So here the fundamental difference till H, here the fundamental difference is EI and here it is ES, and it shifts after H. After H it will become EI and here it will become ES, capital ES. After H, till H, it is capital ES and small capital EI and small ES. So what happens at H? So A, you guys said very correctly that if I have AA fit, AA. So the first letter basically tells us what will be the fundamental deviation. And then there is a second letter which is second digit, A7, G6, something like this. So this G tells me that this is G will somewhere here. G will be somewhere here. And this is the band. This is what the band would be. I'll tell you how to determine the band also, but right now we are just discussing what will be the fundamental deviation. Okay. So this will be the fundamental deviation. Can somebody tell me what will happen with H and H? Sorry. H and H. These two. Any guesses with H and H? It's a tricky one. It will either be flush or it will be just clearance, because what we say is in most cases it will be clearance. In the best condition, if I make exactly both 50-50 or exactly the same diameter, it can be flush. It will just flush, be in perfect contact, but then in most cases what will happen is it will be here or here. So in most cases it has to be clearance, but there can be a condition where it may be flush, just one off case. If I am able to make one right at zero line and this also at zero line. Okay. So any questions here? If you have any questions, just ask me, because so you have gotten the concept what is fundamental deviation, and then we'll do the tolerance band, which you have to identify. So I know the fundamental deviation, I know this EI and ES, but I still don't know how large, how wide will this be, this band be. This band can be this much, this band can be anything, right? If I choose this, say B, this B can be either this or it can be this. That depends upon the what tolerance grade you choose. 1, 2, 3. So the letter tells you fundamental deviation and the number tells you the band or the tolerance grade. So that's how you always give the limits in combination of a letter and a digit. Digit I'll come back to. I'll come to digit. But up till now, have you understood what a fundamental deviation is? So basically this means this is how it looks. And let me just show you the table. So if you want to find fundamental deviation, you have to go look here. This is how what A means, what B means, what C means. A means that A is equal to minus 0.35 D. C is equal to 5.2, D 0.3. Okay. So there is these deviations. There's a formula for these deviations, fundamental deviations. There is a formula for fundamental deviation. And exactly the opposite is for the holes also. Formula for fundamental deviation. Okay. So you get me? Any questions here? So there are formulas. If you can go and look, there will be a formula for this ES and EI. Whichever is the fundamental deviation. Before H, it is EI for hole and ES for shaft. Because it looks like this. See? Right here, this fundamental deviation is ES and EI, and after that it flips. It flips. Okay. So now how do we go do it? So these are the fundamental deviations. Now there is something called a grade of tolerance. So a grade of tolerance is basically something called IT01, IT01 to 16. There are 16 grades, acid level of accuracy. So 01 to 04 is only used for production of gauges, plug gauges, measuring instruments. Very tight tolerance. 5 to 7 is for precision engineering. 8 to 11 is for general engineering. 12 to 14 is for sheet metal and press. And 15 to 16 is for casting general. So it's very coarse. It's very broad. Okay. Then what happens is there is something called standard tolerance unit. And this 1 to 4, 5 to 7, 8 to 11, 12, 14, this IT01 to 016 is defined by this tolerance unit. I'll just show you. There's a table here. See, so IT6 is 10I, 16I, 25I. How do you get this I? This I is nothing but this. This I is the tolerance unit. Tolerance unit is a function of D. And this D is not your diameter. D is not your zero size, right? It's not your nominal size. D is the geometric mean of an upper and lower diameters in this table. So there is a table here. So if D is 5, it lies between 3 and 6. So it will be root 3 times 6. So if D is 5, if my basic size is 5, D will be equal to root over 3 by 6. If my basic size is 10, it will be basic size 5. This is there. If basic size is 10, basic size is equal to 10. Then this will be root 6 and 10, root 60. You get me? So this basic size D is not your basic size, but D is the geometric mean of the upper and lower diameters where your the chosen diameter or the basic size lies. This is a small trick because they have to make all this, which is valid over a large number of diameters. So they have done some statistical analysis and gotten these standards by doing some statistical analysis. So I'll stop here. I'll pick it up again in the next class and show you some of the worked out numbers, which will give you some concepts. But if you have any questions, let's discuss the questions either about the project or about even this class. Any questions you folks have? Midsem, I will have to have a midsem actually. That's what I have been told. So we'll have to have a proctored midsem. During the midsem season, during the midsem week, there would be a slot, I believe. We'll try to have in the same slot. And before that, I need to have a proctored quiz also, apparently. That's what I have been told, that you need to have a proctored quiz as well. So we'll work that out. Although you don't have to worry too much about it because this course is diffused, right? We have lot of we have homeworks, we have projects, so we'll not make very heavy midsems and final exams. We'll try to keep the weightage low for this, and this is actually a project-driven course, so I don't want to make the midsems and the final exams worth a lot of credit. But it will happen in the midsem week. We'll give you some credit for that. Oh, 24th is okay. Okay. So don't worry. I'm sorry, I did not know that it was 20. Submission is fine. So you submit on 24th, but you can get your presentations ready by 23rd, right? Because we have XC slot there. We have our XC slot. I wanted to finish all the presentations in that slot since we have a slot for that. So you can do it on 24th. So submit the report on 24th. Just make the slides and do the slides by 23rd. I thought that Wednesday was 24th, so that's my mistake actually. I'm very sorry for that. Okay. Is that okay? Or you want to postpone it? If you want to postpone it, everybody says postpone, I'll be okay with it. You tell me. If 23rd is okay, fine. If you want to do it on 30th, that also is fine by me. If you feel that you need some more time for that. Let me know. You guys discuss and let me know what you want. So 24th can still be the submission deadline. The presentation can happen later. Whichever way you want. If you're okay with 23rd, it's okay with me. If not, you decide when you want to do it and that should be fine. But what I want to do from now on is that the TAs will meet with the groups which they have been assigned to. Every slot, every Wednesday slot, and you can discuss if there are any issues. So both the TAs can help you, you can report to him what you have done so that there is some compliance on your part. Okay, so that you can actually keep on doing regular work. Otherwise, it will again be in spurts. So, any suggestions? Do you want to give me suggestion right now, or you want to get back to me? What would you prefer? Okay, so Ujjwal, you have to get back to me at some point of time what you want. Whether you want, so you get back to me when you want to do that. Whether you want to present the 24th deadline is final. The report has to be given on 24th because I've been telling you this since long. And the presentations you can do either on 23rd or 30th, whichever day you decide. But from now on, every Wednesday, you have been assigned your TAs. The second sheet of that Excel has the email of the TAs. So you can reach out to your TA, and we'll let the TA know that every Wednesday in the XC slot, you have to meet for some time. You update him what you are doing. It can be reasonably informal. You can just tell him what you have done because he wants to evaluate. And this evaluation has to be a continuous evaluation. I don't want to do make or mar evaluations because then what happens is, and you are busy with everything. So I don't want you to give, I want you to work in a steady fashion, and not everything in the end everything will come at one go, right? So that will be very difficult for you. So I want you to work through the semester so that you don't have a lot of stress in the near the end sems. Okay, that's my suggestion. So what I will do is I'll stop here now, and hopefully if you have any questions, feel free to email. Okay, and get back to me with whatever you have decided. Okay, so thank you very much, and we will see you on Wednesday or Thursday, whatever you folks decide. Okay.